Hello and welcome to my fourth and hopefully final video on the simple platformer programming for the Super Nintendo. So in this episode I will go through a few other various things which I've added to this project. As you can see here we have two new playable characters and our original player here. So I'll now get into what I'm going to go through here. So after the last video I was playing around with the code and added another level, and then I tweaked the first level slightly, and then this created a great slowdown with the code on level 2. I think it was because there was more enemies in there. So this prompted me then that I had to go into code optimization big time to make the program run fast enough. So the first topic I'm going to go into will be code optimization, and I'll show you. First off, I'll bring up the Snes site, which has loads of details of tips and tricks, as they're called. Basically, it boils down to you can't really expect the old consoles to be able to work with C in a nice and efficient manner, really. Obviously, but with the C code, it's obviously converted into assembly language by the compilers. Obviously on these old machines you're going to be limited to what you can actually get out of C, and how the compiler manages to kind of convert your C into assembly code in the background. So I'll go into that shortly, and then I'll also go into our playable characters. Well, I'll put a poll up asking what things should be put in for this video. One of them was directional animation. So I will go through how I implemented it in this project, and it's pretty much the same that I use for all others, really. I'll go into that as well, and then I'll go into what's new, some key changes that are in the game. So first off, I will bring up the Snes tips and bugs to give you, well, rather explain it through how they sort of detail things here. So one of the things to be aware of is when we create large data arrays in C, you need to make sure that they are files not less than 32 kilobytes in size. That pretty much goes for the data arrays that you include as source files as well. I've had issues in the past where suddenly the program stops working properly, and that's most likely down to that there. That's not really what I'm going to be talking about here, though, this bit here. The key things I'm kind of going to go over is what can kind of slow things down here. So one thing to note is with the Snes CPU and loads of the older 8-bit CPUs, signedness. So that's the way that the CPUs handle positive and negative numbers. If you have a signed type, then that means that the type is split in half with half of the range of that type. So for example, a byte, or rather a char if you like, in C speak, is an 8-bit number. Now, if the range of that is 0 to 255, now to emulate negative numbers, what the CPUs do is they half the range, and they say, okay, half of the first half of the range will be a positive number, and then we'll have the other half from 128 onwards, that will be a negative number. So what they do is they set the last bit to 1 whenever a number is negative. So for example, the 7th bit in an 8-bit number, if that's set to 1 and we're using signed numbers, then those are treated as being negative numbers. However, when you are working with signed numbers, there is obviously an overhead to the CPU which can be slower. So if you are using signed types, potentially that can be slower than using unsigned types. One minor change I made in this one was using some unsigned numbers rather than signed for another effect that I had with one of the enemy bats. I've added in like a bobbing up and down when they sort of flap around. Initially I was using signed numbers for that, but I decided against it and used unsigned numbers instead. It creates the same effect. I'll get into that when I go through some of the code. And then this is a key one here. So function parameters. So if I bring up something here a minute, here we go. So this here is a function parameter, and then lots of the functions in the S2D structure have parameters in them. So most of these I haven't changed, but it's best when you decide to optimize, as I have with the level manager modules here, is I have removed all parameters for key functions. So the collision map peak function no longer takes parameters and inside the function call. Instead, we have a load of global variables which are named in such a way that it's clear that they are associated with the level manager module. So now every function call, you have these core parameter variables which you need to fill out first. And then jump back into there. It basically says the reason for that is these function parameters are being passed on the stack. So what the stack is it's inside the CPU, or rather inside the console itself. The machine creates a stack of 8 or 16-bit numbers, and then whenever the CPU jumps from one memory location to another, it first pushes numbers onto a stack, and then it jumps to a new memory location, executes whatever code is there. It then takes those numbers back off the stack, loads it into its registers, and then carries on or returns to wherever the value was before. Sorry, that's not a very good explanation there. I would kind of need to explain assembly language, which I don't really want to go into here. But basically the way that loads of function parameters work is every additional number you put inside a function call, the CPU puts that number on a stack. So it pushes the numbers down in this stack, which is a fixed area in memory normally. And then when the code jumps to the memory address where your code is, or rather when the CPU starts reading from the memory address where your code is, it then needs to pop those numbers off of the stack into various registers to be able to use those numbers to work with, if you like. So by doing that, it's potentially quite slow. So that's why I've kind of gone down the route of removing function parameters from key functions in the game now. And then another key thing here as well is pointers. Now this is a weird thing that's kind of unique to the Super Nintendo, basically, how it's kind of implemented its address space. So its address space here, it takes a 24-bit address space. And then obviously this 24-bit number here, there is obviously no data type, which is 24 bits in size. And then basically going through here, what this basically says is the compiler needs to create a 32-bit number basically to get around the issue of using pointers. Obviously this is very inefficient on the Super Nintendo, and it can also cause issues as well. I'm not going to read through all of this here. I'm going to check all this out. This is the site here. The key takeaway is I've stopped using pointers in the code as well. So there was structures I was using for the game characters. I've now unwound these structures, as I will show you here. So all of the stuff that was previously in a structure is now its own individual global variable now. So what this means is it's a lot faster to work with. Probably doesn't affect the player too much, but the enemies, you get a clearer view of this now if I jump into their code here. So all of their stuff now has been unwound into individual single arrays now. Basically it's exactly the same as before. You can mitigate not using structures basically by just having things in single dimensioned arrays. As long as you give them like a decent naming convention like I have here, then it's not too much of an issue not using structs. This is the same sort of thing you would do on various older computers as well, like I was had in the text on the first sort of slide really. All this means is instead of working with arrays of structures, which are obviously hard for the CPU on the Snes to use, you instead use single dimension arrays as well, or rather in place of. This is the same for the sprite manager class now as well. There's no structures in here now. These are all using core global variables, if you like, just being used as function parameters. The set tile data and palette, they still have function parameters in them as it doesn't really affect these. Most of the time, you would set the tile data and the palette data before the gameplay had actually started. So I've made optimizations which might affect the game while it's in play, rather than things which are done outside of the core sort of game running. So I'll just get back to this now. So yeah, there's it says basically the way that the Snes works with pointers is potentially slow and inefficient, because obviously it has to get the actual address for each type in a pointer. For example, here we've got a number of different types there. These would all internally in memory be sort of unwound into arrays anyway. So by us just having single dimension array strips, if you like, we're kind of helping the Snes compiler to create optimized code for us. And then there's a list here of Shiru's tips. This is obviously about the CC65 compiler, but as the 816 and the Snes is based on the 6502 to some degree, it's its successor to some degree, the same things apply. But then this also applies to most of the old machines anyway. Best to follow these when you need to gain speed if your program's running too slowly. So I won't go through all of these. One of the things here, obviously it says signed types are slower, unsigned char, use it as much as possible. Not too sure about this with the Snes. So one of the weird things that the Snes has is it has like a flag you set in memory to switch it between 8-bit mode and 16-bit mode. So I've no idea whether this actually is true for the Snes or not. Again, without seeing what the Snes compiler actually outputs and going through with like a fine tooth comb, it's difficult for me to kind of know for sure that unsigned chars are the fastest data type to be using. Other stuff I've seen for the Super Nintendo says that it has like a switch where you switch the CPU between 8-bit mode or 16-bit mode. So in theory, if you were using 16-bit numbers in 16-bit mode, then obviously there shouldn't be too much sort of penalty for doing that. But obviously, as we're using C, not assembly, we don't have any control over that as far as I'm aware. So I think that's it for that sort of side of things. So I will now get back to the slides here. So yeah, pretty much all of what I've written here is basically what I've just said. There's nothing additional here that I need to sort of go through here. So we'll get into game actors and animation states. So we've got 3 new characters. I'll show you the first one here. This is the dragon character. This is based off of a Pokemon character. I kind of had a sprite sheet for one of the Game Boy Pokemon games and then made some tweaks to him, and we have this character here which looks pretty cool. This is actually my favourite character. And then one of the things to note here is all of the game characters now have been put into their own individual sprite block if you like. And we have a few different animation frames in here. So we have this frame here, which is the static frame, which is the first one that's shown. And we have a number of frames here for an idle animation. I'll preview all these in a moment. And then we have 2 walk-in frames. We have a bounce frame, and then we have a dime frame here. So I obviously could have added a load more here, but I will go through how I sort of implemented this, and it will give you info on how you may do that if you wish for your own games. So one thing to note as well, for if you're just going to play around expanding or building on this program, then this is how you'll need to lay out your characters. You'll need a 128 pixel block here. The reason why this is chosen here, this size, is because this fits nicely into the way the Super Nintendo lays out its sprites in memory when using 16 by 16 pixel image frames. So as I was saying there, we have one static frame, we have an idle frame here. So basically what this is if you don't do anything for a period of time, then first off you will go into the static state where your character is just standing perfectly still, and then if you don't do anything after a couple more updates, then they go into idle mode where they jump up and down to get your attention. We then have walking frames, a bouncing frame, and a dime frame. So these are all replicated for the 3 new playable characters that I've introduced into the game. And then notice as well that the only direction for them is facing to the right. So we can use a function, or rather one of the core things that the Snes allows us to have, which is we can mirror sprite frames either horizontally or vertically. So in our case here, we're only really interested in flipping them on the x-axis. So if they're facing to the left, then we'll set the flip sprite or mirror sprite horizontally flag, and then if they're facing to the right, we will make sure that that flag is clear. So I will now go through how we would how we kind of implement this. So when we're creating a number of animations for our characters, I found the easiest way to keep track of what they're actually doing is via another state machine. And then I create like an animation state for the character, and then we then need to record some key parts for each animation state. We need to know what the starting frame number is. So if I bring this back across again, and then just scale this into view. So this would be frame 0, this is frame 1, all the way to frame 7 at the end here. So we need to know what the starting frame number is, and then we would need to keep track of how many frames there is for that animation state, and then we need a kind of timer value to say how long each individual frame should be displayed while they're in that animation state. Once we have those key three things, we can create as many sort of animation states as we like. We can only be in one animation state at a time. So I will now sort of bring in the code for the player to kind of explain better what I mean there. So here I have a number of constants here. We could obviously have put this into an array if there were a load of different animation states our character had. For example, if we were kind of had like a kind of like top-down view game or something, then you could have like diagonal movements as well. So obviously we would need to have a lot more data to show that. So here we have the starting frame identification numbers here. So these numbers need not necessarily be the actual location in VRAM where these things are. And the reason for that is when we create our sprite, we pass to the sprite the tile base, if you like. The tile base would be the actual number of that sprite in video RAM, and then all these are kind of offsets from that, just to make it easier to work with them. And then we have a number of other variables here for frame counts. How many frames are there for that? So you'll notice here that the walk and the jump animations are exactly the same. Obviously you could add more frames for all of the characters if you like for your own game, but for this here I decided to make those the same. Rather here the starting frames are the same, and then the frame counts are the same as well. So if I show you the other characters now as well. So we have our token female character here. And then we have our original player here. So as you can see, the animations are the same for all of them. They all have the same frame numbers. This makes it nice and easy to work with. So if you just switch one player out for another, we can literally just copy their graphics into VRAM in the exact same location and not have to have individual code for each character. If I bring the dragon character in as well, you'll see that their frames are exactly the same as well. This just makes it nice and easy to add as many players as you would wish, as long as their frames are all the same. It's just a case of switching one image set, if you like, for another. And then here we have the frame times here. So these times are basically in update ticks. And then we have our list of animation states our player can be in here. So there's a reason why dead is put as 0 here. And then we have the idle state is the kind of lowest normal state for the character to be in. and then we have like a state time here. So when the character is moving around normally, like, so if I walk in here, then we have a state time which is set. This state time is only active if they are in the walk-in sort of state or the static state. Basically what happens is you end up going from walking down to static, and then from static to idle. And then if you walk again, then you go back into the walk animation state. If you stop, then your character will be in the static state for a bit, and then transition back to idle. And then here are the key sort of bits to enable this. We have the animation timer parts here. So as I'm not using the tick timer structures now, we sort of separate the same sort of things that we had before. We have like a timer start and the timer value itself. These are kind of the timer pairs, if you like. And then we have the old animation state and the new animation state. And then we have the frame now value. And then we have the frame start value. So the frame now value would always be 0 to however many the frame count is. And then the frame now value, when we draw our character, is added to the tile base to get the final tile for the character when we eventually draw them. So using those states there allow us to implement various movements. So again, to get a better understanding, you'll probably have to play around with things. So let's go into what else is new. So I've gone through the sprite sheets for the players. What I will show you is as we've split things up now, the enemies now have their own sprite sheet as well, and their own palette as well, whereas before they were sharing palettes. They now have their own palette now. So what this allows is, it means we can get additional enemy types by simply changing the color palette, as I will show in the program here. So we have version 1, so these are the ones which are loaded into video RAM, and then all we take from this image here is the color palette, as there's no need to load this graphics in, as it's exactly the same as this, just different colors. So this is why in loads of the older consoles, the way that they implemented additional game characters was simply by changing the color palette, as there is obviously a limited amount of graphics you can actually have in play at any one time. And then another thing I've done as well is I've increased the player's speed as well. This has the effect of allowing the player to jump further on the x-axis, but it also presents another issue. So the maximum speed last time was 2. Now 2 goes into 256 nicely, 256 being the width of the screen. What that means is it allowed the character to move around and always be able to align to the tiles nicely. Because I've increased the player speed to 3 now, there is a chance of issues with colliding with things now, as the player will no longer be aligned to even pixel numbers. This can be present when you move to the very edges of the screen, and on some tiles as well this can cause issues, which is why I kind of I've made the levels the way I have to prevent issues with that. You'd probably need to play around with that to kind of understand it better. Basically, you kind of want to move things so that they are always kind of aligned nicely with the world they're in. As the player is moving in speed increments of 3, it means it doesn't align to tiles properly anymore. So this can cause issues where if tiles are too close together, you might not be able to fall down a gap because you're not actually aligned correctly to be able to fall down between that gap. And then another thing I've done as well is change the bouncing height when you kill an enemy, as I was finding on some of the other levels which I've implemented. So there's 3 new levels which I've put in, but I was finding that there was a chance when you bounced off of an enemy that you become completely embedded inside one of the platform tiles, as the collision checking was not adequate to prevent that. This is a possibility that can occur. The more complicated you obviously make your game, the more potentials there are for issues which you have to overcome. So this could have been fixed with a load of additional checks to make sure at the end of a bounce or a fall that the character wasn't completely inside of a tile. But obviously the more checks that you have to do each update, the slower things can get. And then another thing I've put in as well, like I said, is we have some additional main states in the game now. We have now got a choose player screen and a game win screen. The reason why I put the game win screen in is obviously we all want to be able to complete a game. So it's good to have a screen that shows that to the player once they've completed all of your levels. So that is now a main state in the game as well. So basically, if you complete all of the levels, then once the last level is cleared, we do a check to see whether you have done that. If you have, then main state is then set to game 1 initialize, and then the main states are pretty much exactly the same. So if I go into the choose player here, move that over here, it pretty much looks identical to some degree to the title screen. The key thing here is we have the functions declared in main. So this is the external prototype here for init. And then, sorry, this is the one here. So these are the 2 sort of core functions which are declared externally here in main. And then in here we have a timer. Happy to use the struct timers only inside the title screen areas, because obviously there's nothing speed dependent happening inside of these. So these were used inside of there. So that's those there. So yep, choose player states there, and then there's a new life counter added and a high score check on the title screen as well if you've beaten a global high score. So in the header file here you'll see there is a high score of 200. This is the starting high score to beat, and then every subsequent play of the game you'll then have to beat whatever value is stored in the G for global high score variable. So some other things in here. I've removed most of the structs, like I said. I'm not using the entity struct anymore. This is still used inside of the level manager because again this isn't going to be affecting the speed of anything. These are not used anywhere where speed is an issue either now. And then we have our player types here, so I'll quickly go into how this was implemented. So these two functions here are for choosing our player here. This is the location where they should be drawn on the choose player screen, and this just updates the graphics for each player chosen going off of the player type variable here. And then these core variables here are for a rectangle collision function here. Now, I don't think I'm going to go into any more code now. What I'll instead do is I will show you first I'll show you the update I made to the game before the optimizations, and then you'll see the reasons why the optimizations were needed, and then I'll quickly show you the final product of that with the optimizations. So this is version 1F here. So I'll show you some of the slowdown that occurs with this. Some of the slowdown occurs with the jumps. This is a redesigned version of level 1. One other thing as well is I've removed this tile type here. Initially I was going to have destructible tiles, but then I decided that this was an additional overhead to get rid of. So I will still runs pretty decently on the first level here, and on the second level here there is a lot of slowdown, as you can see here. Not sure whether that was whether the slowdown was due to the structs or not. Oh yeah, and then you'll see that for each additional enemy that's actually killed, the game speeds up. So another thing I'll quickly go into as well one of the other things you can do to speed things up, which is what I've also done here, is that version there, it was updating all of the enemies in one chunk each update. And it also had a maximum of 10 enemies on that version as well. One of the things I've done on this new version is added a maximum updates per frame. So what this means is we have a variable which tracks which enemy is active. So if I come down to the update frame here, so all of this has been rewritten to work with the optimized code now. So instead of updating all of the enemies every frame, instead we only update this number here, which in this instance is 4. And then each time through the loop here, so this variable here keeps track of which enemy to work on next. As everything is, all of the enemies are split between various, or all of their properties, if you like, are split between various single arrays now. To access one, we literally just take a number from each of these arrays, but as they are single arrays, it's not so much of an issue for the compiler to get the Snes to work with, whereas using the structs was slow. And then in this case, all what happens is each update we only process a couple of the enemies, so they don't all move at once. Only a couple will move one update, and then the rest of them will move the next update. This is something you can do to gain additional speed in your game as well. However, when it comes to drawing them, you will have to draw them all if they are on the screen, that is. Again, I'm not going to go into every optimization that I've done here, but a lot of the code has changed, so I would definitely check it out to see what has gone on there. So I will now get into the final version here, which is the one I will be posting the source code up. So you'll see the names change now. Obviously, we have a number of different characters now, so only fitting to have a number of a change of the name of the game. So when we press start now, we have our choose player screen. So using left or right, we select our player. As you can see, by literally quickly copying the new graphics into video RAM, when we change the player, this is nice and fast. So one thing you'll notice here as well is the bats now are using a lookup table for their there you go, that's the animation states in play. That's the idle state there. Then if you walk them around and then stop, go from static to idle. So have a play around with the different timings. So there are 3 levels, and the game can be won. In fact, I've still got something else I need to remove. I additionally started the game with like a higher score, so I will need to remove that as I was using it to test the high score function. So I won't go through all of the levels or the game 1 screen. It does pretty much run at the same speed as this throughout now, which is good, and that pretty much concludes this video. If you've got any questions or you find any bugs that I've not disclosed here, then obviously let them know in the comments below, and I will go into them further. So yeah, let me know if you think I should turn this into a proper faux game, as I could well do. So some things for yourself if you are going to build off of this. You could always put like a background in on one of the on the other layer, which I haven't been using here. Some other things you could do, maybe some music possibly, maybe some different tile types, I don't know. There's a whole load of stuff you can do. And then to design the levels, all I was using was pictures. So if I open up, pretty much the same from the last videos where I showed how I was creating the levels. So you just design the level like this here. The template was in one of the other videos, I believe. And then you're literally just converting that into numbers here. Each pixel basically represents a number in here, and then each of these numbers are obviously correspond to tile types. So yeah, hopefully you've learned enough to enable you to make your own platformer now. So thanks for watching, and I'll catch you next time.